Hello, everyone. I'm Glen Junor, one of the postdoctoral impact fellows at the MIT Climate and Sustainability Consortium. Today, I'm going to share recent developments and design principles for the topic of phase change carbon capture for about 15 minutes. But before we get into the chemistry, I just want to frame our discussion a little bit. According to the Intergovernmental Panel on Climate Change, humanity currently releases roughly 42 gigatons per year of CO2 equivalents. To reach net zero, we need to cut this number to 7.6 gigatons per year by 2050. Here I'm quoting the International Energy Agency, but other organizations have similar numbers. And we must do this while still allowing economic growth. If we hit this target, those 7.6 gigatons that remain are going to come from hard-to-abate industries, and we will need to capture and sequester those emissions. However, current CCS capacity is low. It is shown here to scale. We can zoom in a little bit. As you can see, the current worldwide capacity of carbon capture and sequestration is only 40 megatons per year, which is much lower than what we need in 2050. We must grow to 190 times the entire world capacity in only 28 years, which is a feat in and of itself. Current technology on point source capture requires approximately $1 trillion per gigaton. And that's after 100 years of optimization of this technology for natural gas processing and scrubbing emissions of coal power plants. This yielded front runners like monoethanolamine, diethanolamine, and piperazine, which have seen deployment on very large scales, like megatons per year on a single site. But we have to remember that these were developed largely for natural gas processing or coal combustion power plants. But 2050 projections of some of the most critical, hard-to-abate industries like cement, steel, and aluminum production are likely to consume almost all of our hard-to-abate budget. Keep in mind, I'm only showing direct process emissions, not the emissions associated with the heat and power used to produce these materials. It is not obvious that solutions developed for natural gas processing and coal combustion are going to be adequate for these industries. I'm not saying it won't work, just that assuming these technologies translate despite only minimal deployment so far poses great risk to our needed 190-fold scale-up. And it is these factors that are motivating R&D on different types of carbon capture, one of which is phase change capture, which we're discussing today. Before I dive into recent literature, let me explain the concepts of phase change capture. We have our mixture of gases, including CO2. These flow over a contactor, and CO2 is selectively absorbed by the solvent. This capture is facilitated by some sort of binder, commonly a base. In a phase change system, the base CO2 adduct is no longer soluble in the original solution. This precipitation allows for separation of the base CO2 adduct from the original solution. The precipitate can then be sent into the regenerator on the right. Now we can apply heat to only the CO2 containing stuff, which reduces the sensible heat requirement on the capture plant. After release of pure CO2 in the regenerator, which can then be sent away for sequestration, the binding material can be put back into the capture tank and resume capturing. Another benefit of a phase change system is the increased capacity. Since the precipitation is occurring, capture of CO2 continues to proceed as it cannot reach an equilibrium. Okay, with the basics out of the way, let's dive into the literature and commercial examples. I think the most well-known commercial example of phase change capture comes from the company Carbon Engineering, founded by David Keith, a professor of chemical engineering at Harvard. Their system is based on two reactions. First, potassium hydroxide reacts rapidly with CO2 to form potassium bicarbonate, which is soluble. But to prevent heating a large volume of aqueous potassium bicarbonate, Carbon Engineering reacts potassium bicarbonate with calcium hydroxide to regenerate potassium hydroxide and produce an insoluble calcium carbonate, which is basically limestone, and precipitates out. Now, calcium hydroxide is not used to capture CO2 directly because it reacts too slowly. Thus, potassium hydroxide and calcium hydroxide are both necessary for good economics. The calcium hydroxide can be regenerated by exposure to 900 degrees Celsius and steam. David Keith gave a recent talk here at MIT about the 1 megaton per year capture plant that they're building in Texas, which just finished front-end engineering and design and is starting construction. He said it looks like the cost of direct air capture is roughly $300 per ton, which is pretty remarkable for direct air capture, which often exceeds $1,000 per ton. Also, this facility has megaton capacity, which is way more than any other direct air capture plant to date. To keep track of these concepts, I made little icons. This one represents our understanding that lattice energy, the crystal structure, kind of shown here, lattice energy can be the driving force for capture. Here it is referring to the lattice energy of calcium carbonate driving the reaction. So Radu Kustelson from Oak Ridge National Lab aimed to create a drop-in system that takes advantage of all the engineering advancements from carbon engineering, but removes the high temperature required by the calcination reaction. His parallel two-reaction scheme involves glycine, or gly, as the initial capture chemical. Here's the chemical structure of this amino acid, glycine. Now, glycine acts similarly to carbon engineering's potassium hydroxide and reacts rapidly with CO2 to form a soluble atom. Kustelson then uses a bisaminoguanidine, BIG, to precipitate out the CO2. Here I've shown the pyridine derivative, PyBig. PyBig functions like calcium hydroxide in carbon engineering system and precipitates out the CO2, regenerating the original capture chemical, which in the Kustelson system is glycine. I have only shown PyBig here, but they have developed several that can be used for various applications, whether it's flue gas or direct air capture. The key is that PyBig forms strong hydrogen bond networks to carbonic acid, causing crystallization, and a much lower regeneration temperature of around 120 Celsius, which varies based on which bisaminoguanidine is chosen. So we learned that by substituting a crystal lattice of strong bonds, like that in the calcium carbonate lattice, for weaker intermolecular interactions, like the hydrogen bond networks of PyBig, we can reduce the temperature requirement of regeneration. So David Hildebrandt at Pacific Northwest National Lab has been investigating many avenues of carbon capture, only one of which is phase change. For that, he seems to focus a lot on one reaction system, particularly ones that do not have water as a co-solvent. Recently, his group started to focus on aminopyridine derivatives, AMP, for a low viscosity water lean capture solvent. The phase change occurs because AMP CO2 adduct is not soluble in the liquid aminopyridine, causing precipitation directly. No second reaction is necessary. And the regeneration temperature of these solids are similar to the Kustelson systems at 150 Celsius. From the Hildebrandt group, we then learned that the formation of intramolecular hydrogen bonds can also induce a phase change. Seiji Yamazoe's group at Tokyo Metro University published a very recent study along similar lines. A diamine called IPDA dissolved in water undergoes a phase change upon exposure to CO2. We can understand this by considering possible hydrogen bonding positions in the diamine versus the CO2 adduct. The diamine can form many hydrogen bonds with water, making it soluble. However, the reaction with CO2 occupies many of those positions. The drastic reduction in the number of possible interactions, combined with a somewhat rigid hydrophobic backbone, leads to an insoluble product. Unfortunately, the molecular characterization in this paper is limited, but I am proposing that this macrocyclic interaction is occurring in a manner analogous to the Hildebrandt work. Remarkably, the regeneration temperature of the precipitate is only 60 Celsius, which is much lower than reported in the other studies. If my hypothesis is correct, then this could be understood that the macrocyclic species formed by reaction of IPDA and CO2 forms a much more weakly bound CO2 when compared to a smaller ring like that found in Hildebrandt's aminopyridine. The last concept I want to highlight today comes out of IFP Energy Nouvelle in France, called the DMX process. They use a blend of two amines, DEEA and AEEA, shown here. The primary amines react with CO2, and the tertiary amine likely holds the proton, inducing a phase change. But what is remarkable is that the phase change results in two liquids rather than a liquid and a solid. The products form even better hydrogen bonds than the starting amines, essentially pulling all the water to the CO2-rich portion of the liquid. The original amines are immiscible with that solution and simply float to the top. Those can be sent back to capture more CO2. Then liquid handling techniques can take the CO2-rich portion off to the regenerator to be heated to 120 degrees C. Now, one drawback is that water is attracted to the carbamates, meaning that we still have to spend energy heating up those molecules, reducing the benefit of the phase change system. But what is impressive is that it's possible to induce a liquid-liquid phase separation, so we can take advantage of liquid handling techniques. Okay, so I've given an overview of some important recent developments on this type of carbon capture, but to start off our discussion today, I want to propose a vision for an ideal future of phase change capture. Can we take lessons from the DMX process out of the IFP Energy Nouvelle to have the phase-separated product of CO2 capture be a liquid? If so, we could use liquid handling machinery. But if this liquid is immiscible in water, we could better retain all the benefits of reducing sensible heat requirements. And perhaps we could use intramolecular interactions guided by the Hildebrand work. But we need to keep viscosity low so pump duty can be minimized. Now, I didn't go into this today, but other work by Hildebrand showed that tuning inter versus intramolecular hydrogen bonding can have enormous impacts on viscosity. And can we do all this while maintaining low regeneration temperatures, perhaps drawing lessons from the Yamazoe group and designing for macrocyclic interactions? And is it possible to choose starting materials with high boiling points to minimize the amount of chemical emissions caused by any process that we create? Okay. So thank you for listening to this presentation today. I hope those interested in working on this topic can take lessons from this to increase the impact of their work and help move us more quickly towards our net zero goals. Have a great day.